Meet Gottfried Wilhelm Leibniz, the architect of the modern mind. Bridging classical Enlightenment philosophy and the dawn of computation, Leibniz envisioned a universe structured through pure logic and mathematics. As illustrated in this dual portrait, his visionary work seamlessly connects historical mechanical ingenuity with our contemporary digital world, encoding reality into binary foundations that laid the groundwork for modern computing. Gottfried Wilhelm Leibniz stands as the ultimate polymath, the last universal genius. Spanning 1646 to 1716, his astonishing mind interconnected vast realms of human knowledge like precision clockwork gears, mathematics, computing, physics, philosophy, jurisprudence, diplomacy, and geology. As French philosopher Denis Diderot famously observed, few thinkers in human history read, studied, or wrote as prolifically as Leibniz. Had his vast ideas carried the literary flair of Plato, the philosopher of Leipzig would cede nothing to the philosopher of Athens, leaving behind an intellectual legacy that spanned the entire horizon of human understanding. While studying under Christian Huygens in Paris, Leibniz tackled the challenge of capturing continuous motion and space. On November 11, 1675, he achieved a breakthrough by defining integration as the summation of an infinite series of infinitely thin rectangles under a curve. Blending geometry and algebra into a revolutionary framework for calculus, his work culminated in the landmark 1684 publication, Nova Methodus Pro Maximus et Minimis, forever changing how we measure change. Leibniz crafted a mathematical notation so perfectly attuned to its subject that it mirrors the logical operations of nature itself. At its core is the expression of the integral of y with respect to dx. The iconic long s derives from the Latin summa, representing the summation of an infinite series. Within this framework, y defines the function's height at a given point, while the differential dx denotes an infinitely thin slice of space. By unifying these components, Leibniz created an enduring symbolic language that seamlessly translates the continuous geometry of the natural world into clear, calculable logic. The calculus priority dispute contrasts two distinct visions of mathematical breakthrough. Isaac Newton constructed his method of flux ions around motion, time, and gravity, producing a notation that ultimately isolated British mathematics for a generation. In contrast, Gottfried Leibniz approached calculus geometrically and algebraically, focusing on space and area. By crafting an elegant notation using dy, dx, and the elongated s, Leibniz provided an intuitive, highly expedient framework that outlasted the historic rivalry to become the global standard in mathematics today. Driven to reduce all logical deliberation to pure calculation, Leibniz established the foundations of binary arithmetic. By mapping numbers into just two fundamental states, one for presence and truth, and zero for absence and falsity, he devised a system of discrete logic. Conceptualized nearly 3 centuries before the first electronic computer, Leibniz's binary framework laid the theoretical blueprint for the modern digital age. Leibniz bridged abstract philosophy and physical machinery with the calculus ratiocinator, designing the world's first true four-function mechanical calculator in 1673. This framework automates reasoning through a clear progression, refining messy human thought into precise logical symbols, translating those symbols into calculable binary code, and executing the final operations through rotating mechanical gears. By physicalizing his logical concepts, Leibniz proved that human deliberation could be mechanized. In 1686, Leibniz challenged the Cartesian model of motion, exposing m multiplied by v as physically flawed for violating conservation laws in collisions. Recognizing that motion extends beyond simple pushes and pulls, he introduced the concept of vis viva, or living force, defined as mass multiplied by the square of velocity. This breakthrough revolutionized physics, serving as the direct precursor to our modern understanding of kinetic energy and the law of conservation of energy. Between 1680 and 1685, Leibniz served as an engineer in the Harz Mountain silver mines, attempting to drain flooded shafts using windmill-powered hydraulic pumps. Though technical limitations and worker resistance ultimately thwarted the mechanical project, his time spent deep underground transformed his view of the natural world. Ceasing to see rocks merely as static stone, Leibniz began reading Earth's subterranean strata as a historical archive, marking a profound shift from practical engineering to deep geological time. In Protogaea, 1691 to 1693, Leibniz united geology and paleontology to decode the history of our planet, declaring that nature produces no fakes. He hypothesized that Earth began as a molten, cooling globe, recognizing that subterranean rock strata represent a sequential, historical record of deep time. Crucially, he proved that fossils were the actual petrified remains of living organisms, debunking the belief that they were mere mineral oddities. With this pioneering vision, Leibniz transformed the Earth's crust into a readable archive of natural history. In 1714, Leibniz's employer, the Duke of Hanover, ascended the British throne as King George I. Embittered by the calculus dispute with Newton, the king ordered Leibniz to remain behind in Germany. Isolated from court, struggling with failing health, and misunderstood by his peers, the great Polymath passed away in Hanover on November 14, 1716. Tragic in its quietness, his death went largely unacknowledged by the very academic societies he had devoted his life to building. Leibniz's seemingly fragmented pursuits were not mere hobbies, but the foundational pillars of the modern world. His continuous mathematics powers physics and engineering, while his work on physical energy anchors the law of conservation of energy. Through binary arithmetic, he established the core foundation of computer science, and his insights into geological strata and fossils gave rise to modern earth sciences. Leibniz dreamed of a universe written in a calculable code. Today, we live in the world he designed.